In this video, we are going to talk about CO2 migration in heterogeneous rock systems. In the process of decarbonizing the global economy, there is some industries that are harder or near impossible to fully decarbonize. In these cases, we can resort to carbon capture and storage to safely store them underground instead of releasing them into the atmosphere. Carbon capture and storage, in short CCS, is a process by which CO2 from industrial installations or natural sources is separated before it is released into the atmosphere. Afterwards, it is transported to a long-term storage location. One of the CO2 storage sites is Sleipner, located in the North Sea. At Sleipner, CO2 is injected into a deep saline aquifer. This study focuses on the reservoir rock, where the CO2 plume is formed within the so-called Utsira Formation. The sandstone in the Utsira Formation is not uniform. It contains many thin shale layers, which strongly influence how the injected CO2 moves underground. Because of these shale layers, the injected CO2 at Sleipner is trapped in 9 separate layers. Over time, as pressure builds up, the CO2 can break through a shale layer. When this happens, the CO2 finds a new pathway and moves upward in the next layer. To better understand how CO2 breaks into higher layers within the reservoir, we created a series of models inspired by the Sleipner site. Each model represents a small part of the reservoir where we tested different arrangements of shale layers. In the stable cases, the shale layers are less connected, allowing CO2 to move more easily. In the layered cases, the shale layers are more connected, which makes CO2 migration more difficult. We also vary the proportion of sandstone and shale, as you can see in the figures. Finally, the fifth case represents a reservoir made entirely of sandstone. On the right, you can see what the sandstone of the Utsira Formation looks like in reality. We compared results from a commercial simulation tool, in our case OpenFlow, with a simpler invasion percolation method. The commercial software includes detailed flow physics, whereas the invasion percolation method simply looks for the next neighboring cell with the lowest entry pressure for CO2 to invade next. By running multiple simulations per each case, we can see how heterogeneity impacts the total gas saturation at breakthrough. More sandstone results in more CO2 in the model. There is also a clear connection between the stable cases, where the shale is less connected so CO2 enters easier as well, and the layered cases, which result in slightly lower total gas saturations. While invasion percolation shows some similarities to the flow simulations, its simplicity limits how closely it can match them. This work showed that the right conditions to use a simplified modeling approach is necessary to successfully calibrate invasion percolation models.